I was asked to introduce Tom, which, you know, saying he needs no introduction is like kind of obvious, especially since I think all of you just heard him give the introduction to this. Is that true? Is there anybody that didn't hear the talk that he gave in Frontiers of DA? Okay, good. So, so instead of introducing him, I will say a couple of things. So one is, again, I think most of you might know this, that, you know, we're going to hear from Tom Keelin, the mathematician, about this new and, you know, he has a double life as an actual practicing decision analysis analyst. And yesterday, I think many of you heard him talk about actually not just helping clients make money or lose money, actually helping himself and his friends do so. I mean, that's serious. And more than that, he was actually using Metalog Distributions. So, you know, this is not like some airy-fairy mathematical concept. It's already being used in very real applications. And he also mentioned that he complemented the implementation of the Metalog Distribution in the Analytica software, which my company produces. But I will warn you, if you look at Analytica and search for Metalog, you will not find it, because we came up with a better name for this distribution. I mean, really, you know, there's the Gaussian distribution named after Friedrich Gauss, and there is the, well, you know, I won't go through all of them, but most decent distributions are named after their inventor. Of course, Tom is way too modest to do that, but for the rest of us, it is the Keelin distribution. And, you know, if you look through Analytica, that's what it's called. Anyway, so enough. Tom.
I've said for this group, the first probability distribution is created by decision analysts for decision analysts. I think that's true. But more broadly, I would say that it's the first set of probability distributions created by Bayesians for Bayesians. It's never happened before. And why do I say that? Let's see if this, that's funny, this was working just a minute ago. Pardon me?
Click on your screen.
Click on my screen. Okay. Oh, thank you. Okay, good. All right, so this is, I'd say this tongue-in-cheek, this is my short history of continuous probability distributions. Interesting, it all started around the 1750s in two parallel tracks. The normal distribution was first published in 1756 by a fellow named de Moivre, a Frenchman. The notion that probabilities can be any shape was first published, or first invented in effect, as state of information by Bayes, and then further developed by Laplace in the 1700s. The next big milestone in the development of probability distributions, in my view, was Carl Pearson working in London around 1895 to 1915. And his objective was to modify the shape of the normal distribution in a way that it could fit different shapes of data. And particularly, he wanted to be able to have skewness and kurtosis flexibility, that is, leaning one side or the other, and the fatness of tails. And he wanted to have flexibility to match that. He put together a set of equations for modifying the differential. I'm going to say some mathematical words here. If you don't know what they mean, it doesn't matter. But he put together a set of distributions by modifying the differential equation of the normal distribution, where he replaced the otherwise constant sigma squared, the variance, with a quadratic in the variable of interest, thereby having two new parameters that he basically added to the normal distribution. The solution to that differential equation is called the Pearson's distributions, and those distributions include the normal itself, the student t, there's a Pearson type 4, the gamma, the chi-square, the inverse chi-square, the inverse gamma, the uniform's a special case, and that is today the gold standard, considered to be the most widely flexible distributions in the world. I think what has happened, and it's really different with the introduction of QPDs, and that's the broader class I mentioned in the previous talk, and it includes the Metalog distributions in particular, is it's the first time in this 250 years where we've had a set of distributions that are infinitely flexible, in addition to being easy to use. And they're designed for use by Bayesians. And you don't have to come up with complicated moments and try to fit complicated equations to and then end up with distributions that don't fit very well anyway, right? This is a whole different realm where it's the first time us Bayesians have had something that's for us. Okay, now why are the Metalog distributions so unique and so different? And why do they have these desirable properties? I mentioned in the last session a little bit like least squares or something. You know, you can use it for lots of things, but least squares has a very a set of stable and highly desirable properties that make it useful for all kinds of different things without getting into a heck of a lot of trouble. Metalogs are the same way, and they are this. If we accomplish just one of these bubbles that I'm going to show here, or one or two, it would have been a research success. To have accomplished all of them and have Metalogs be the subset that's right in the center of all this is an extremely unusual thing, and that's why I think it'll be around for a long time. First of all, it's highly flexible, okay, and I've just mentioned that. But secondly, it converges. It's like a Taylor series, you'll see, but it's for probability distributions. And if you add enough terms to it, it will converge to any distribution you put up against it, anything at all. We can prove that it's a so-called analytic function with a radius of convergence from probability equals 0 to 1. So, and I know that's gibberish for a lot of you, but what it means is it can converge to anything, okay? Not only existing distributions, but also you know, data from any source that you might have. It's parameterized by data. That's a huge, huge advantage. It enables you to avoid the nonlinear curve fitting and parameter estimation that goes on with almost all the other probability distributions in the world. And of all the literatures that have ever been written on probability distributions, probably 25% of it is just about parameter estimation because it's such a difficult process. Here it's easy. What else? Any boundedness. With the Pearson distribution, if you get your skewness and kurtosis, you're stuck with the bounds. You can't change the bounds. So you end up artificially cutting something off if you want a bounded distribution, for example. Here you have a choice of boundedness. We've got a simple, and all this is with very simple closed form equations. There are no intractable integrals, there are no gamma functions, there are no beta functions of the first, second, or third kind. There are all these complicated statistical functions in other distribution families. There are none of those here. Isn't that nice? That means you can program it yourself in Excel, although you're not going to have to, but it means it's cross-platform compatible in a very simple way. It has a closed form f to the minus 1, or what's called a quantile function, which means that x, your variable x, is a function of whatever probability y you specify. What that means is you can put a random number in there and simulate it like crazy in closed form with completely simple equations. Well, what's that? Okay. Now, I would say there are other leaves I can put on this. Maybe this is a flower. I can put other petals on the flower here. And these are research topics that have not yet been written about. All this stuff has been written about. But there's a whole set of things now about multivariate metalogs, conditional metalogs, Bayesian inference in closed form, adding up mean, variance, and skewness for a number of independent variables to get mean, variance, and skewness of the sum, and be able to parameterize a three-term metalog in closed form with that. So there's lots, sum of log normals. We can do sum of log normal distributions in closed form. That's never been possible in the history of mathematics. So there's many things that haven't been published that are still coming here. And, but today I've chosen, in the short amount of time we have, to limit it to what is already published and currently available. All right. Here is the equation of the logistic distribution, okay? This is the start of the Metalog. Metalog is short for meta-logistic. That is a generalized meta meta-logistic distribution where we can modify the shape. Look at this simple equation. I love this equation. I was always intrigued with it because it is so simple. It's the simplest of all, perhaps, the probability distribution equations. Mu there is the mean and the mode. And the median. S is proportional to the standard deviation. The log of y over 1 minus y, that's the log odds ratio. And whenever I say y in this presentation, I mean probability. I mean the probability that's on the vertical axis of the CDF. X is the variable that's on the horizontal axis, okay? So, and the logistic distribution has been known for a long time. There have been whole books written on the logistic distribution. And in fact, This distribution is the backbone. It is the sigmoid curve that is the most widely used backbone in artificial intelligence. So it has many, many uses, and it has had for a long time.
Tom?
Yes?
But that x equals y is not customary in probability, and you've got to make that transition here.
Yeah, I'll explain that.
Yeah.
Thank you, Sam. Yeah, you're used to seeing probability distributions that are y as a function of x, but this is a conscious, to choose this function to modify is a conscious choice. I wanted x as a function of y so you could simulate it totally easily, okay? Now, let's do a thought experiment here. And this was the thing that originally, it was the thought experiment that led to the whole development of the Metalog family. That S in that equation, we know, corresponds to standard deviation, okay? And what if instead of that S being a constant, what if as you moved from left to right on the probability distribution, what if that S were continuously increasing in some smooth way? Then you would naturally expect, wouldn't you, that you'd end up with a distribution that is skewed to the right. Does that make sense intuitively? Sure. And if that S were systematically decreasing as you went from left to right, then you'd end up with a distribution that's skewed to the left. What about that mu? That mu controls the center of the distribution. So suppose that mu is continuously increasing from left to right. Well, now you're sort of fuzzing up where the center of the distribution is, and what that would do is, wouldn't it intuitively create a fatter distribution with shorter tails? Turns out it does. So the idea that we originally started with is that we would make this S a function of y, because as you move from left to right, y is going from 0 to 1. And we started off with just these terms. Forget about these. We started off with a simple linear function there, expanding those two parameters with a linear function. That, in fact, is the definition of a 4-term Metalog distribution. And we found, and that was even what we had when I submitted my first draft paper to the Journal of Decision Analysis, and the referees came back and, you know, very challenging set of comments and working it through and responding. And at some point, it came to the realization that we could make this a whole power series expansion. It could have any number of terms at all, both on the mu and the sigma. That is the complete mathematical definition of Metalog distribution, of the Metalog quantile function. Now, this thing, this expanded distribution, notice that it's a linear series of terms. That's part of the design. That makes it easy to fit to data. And secondly, notice that these are very simple forms. It only includes power terms and log-odd ratio terms. This thing is differentiable, so you get a nice, smooth, closed form density function. All right, so now let's talk about how and why. So when you combine all of that, a Metalog distribution is like a Taylor series. It can have any number of terms at all. You don't have to memorize this equation, but it's all perfectly well defined. And again, it's just logs and power terms. It's that simple, okay? And every time you add another term, what you're doing is you're adding more shape flexibility, and more and more subtleties in shape are you able to capture. Also, when you add another term, if you add too many terms, you can overfit, and we'll talk about that toward the end. So now let's just look at what happens as you add a couple of terms here. Now the first two terms in the Metalog equation are a logistic distribution exactly, and so if you didn't have any other terms, you'd always get a logistic. If you add that one simple term, which is a constant A3 times that y minus 0.5 times the log odds ratio, just by adding that one simple term and varying A3, you get all those different shapes. Okay? Wow, how simple. And I'll say where these A constants come from in a minute. The fourth term, but anyway, the third term adds skewness. If you add a fourth term, now this fourth term here is the same equation, but now you've put another plus sign there, adding this. If you look at this, that's linear in y, okay? That is a uniform distribution. And if all the other terms were 0, you'd have a uniform distribution exactly. Therefore, the uniform is a special case of the Metalog, as is the logistic. If you set A3 to 0, then, and vary this A4, you get all those shapes. And all those shapes basically go from basically student T-like distributions with very fat tails down right through, you come up with distributions that look almost exactly like a normal, all the way down to the uniform distribution exactly. Okay? You don't have to memorize any of these equations. I'm just trying to show you how much shape flexibility you get by having just these 4 terms, right? And that says nothing about adding terms 5, 6, 7, 8, 9, 10, and so forth. All right. So this now, and then where do these A constants come from? Well, it turns out if you have a set of data here, like shown on that CDF, the 10, 50, and 90 points are 40, 50, and 70, well, and if you constrain your system by a curve that runs through those points, you have 3 equations and 3 unknowns. Simplest thing in the world to solve. 3 linear equations and 3 unknowns. Simple to solve. Those A constants are determined exactly by those 3 points on the distribution, and the distribution runs through all of them. So that's it. And every Metalog distribution now corresponds to 2 very simple equations. One is the equation of the Metalog distribution itself. That's a 3-term Metalog. And then the other is just the derivative of that. Actually, the reciprocal of the derivative gives you the density function. But that is, again, it's a simple closed form thing that you get just by differentiating that equation up there. And all of this is published, and all of the, the exact additional terms you get and so forth. Now, I said that you could have any bounds you want. You can have an unbounded distribution, like the normal or the logistic. You can have bounded distribution. How do we get to all of those? Well, there's an exact analogy between, as you know, you probably know, a log normal distribution is defined as the distribution over a variable whose log is normally distributed. Well, you make exactly the same definition for a Metalog. A log Metalog distribution is defined as the log of a variable that's Metalog distributed. And if you make that transformation, you end up with a distribution that has a lower bound. And all that does is it takes that basic Metalog equation, and it's the e to that power gives you the distribution. Very, very simple. So now we got exponential distributions in here, but still no gamma distributions or betas or anything else. If you want a bounded Metalog, it's the same idea. The logit, defined by this equation as Metalog distributed, leads to this. And again, very simple closed form function of the original Metalog. All right. So we now have defined bounded, semi-bounded. Now, let's just do quickly a little bit of demonstration of flexibility. So there is, let's see, I can't see what I've got here. There's a 2-term Metalog trying to approximate a normal distribution. It doesn't look that good, but if I make it a 4-term Metalog, it's closer. By the time I get to 6, you can't tell. 8, 10, what does that look like at the density function? There's the 2-term, okay, relative to the normal distribution. Doesn't look very good, but by the time.
2-term straight logistic then?
Yeah, it's straight logistic. And then 4, 6, 8, 10. And it comes just like a heat-seeking missile, it just converges in on the shape of the distribution. Suppose you start with, this is a log normal distribution. How's a log Metalog do for that? Well, there's a 2-term approximation. I just took 100 terms, or 100 points off the log normal distribution, used that to parameterize the Metalog in this case. In all these cases, 4, 6, 8. By the time you get to 10 terms, you can't see the difference. How about this, huh? Here's a generalized extreme value distribution, a Weibull distribution, in fact. You can pick anything you want. There's the 2-term approximation, 4, 6, 8, 10, right on top. Okay, you'd think this would be hard. This is a U-shaped beta distribution, a skewed U-shaped beta distribution being approximated by a bounded Metalog. Even with 2 terms, it's pretty damn close. 4, 6, 8, 10. We could go on doing this and on doing this, but the theorem is that no matter what distribution you start with, the Metalog will converge to it as a mathematical fact. All right? All right, so now let's go to a couple of examples, because the point of the Metalog is not to converge to other distributions. The point of the Metalog is to be able to represent data and give you shape nuances about what that data consists of. So here we have an example of 3,400 data points, catch and release of steelhead trout on the Babine River in northern British Columbia. And you can see these beautiful fish. That one there is probably about 20 pounds. We got the weight records for a lot of these fish, and that's the data for that many fish. And you can see we approximated that. We did what most fish biologists would do. You approximate that with the best log normal you can. You know, weight has a lower bound of 0. But then we also approximated it with a Metalog, and you'll see how that goes. But there's a fact about steelhead that's important to understand. They're born in the river. They go out to the ocean. They fatten up a bit. They come back up the river to spawn. They do not die like Pacific salmon. In fact, after spawning, they go back down the river, go back out into the ocean, fatten up for another 3 or 4 years. They come back up the river to spawn a second time. So any of the fish you catch in the river and release are either so-called one-salt fish, it's their first time back up the river, or they're two-salt fish, or a very few are 3 or 4 salt fish. But the reason I'm telling you this is because fish biologists, if you were to ask them, have really no idea if you say, what's the relative fraction in the river of one salt versus 2 salt fish? How can you tell? Because the fish look the same, right? What's the relative difference in weight? How much weight does a steelhead gain between its first trip up the river and its second trip up the river? Well, these are completely unsolved questions. Okay, now here is the histogram of those 3,700 points. That's what the histogram actually looks like, okay? That's the data. This is what you would get to if you approximated that data with a log normal distribution. All right? But what if you put a Metalog on it? Well, there's a 2-term Metalog, 4, 6, 8, 10. Notice how the Metalog converges to the shape of the data. And what do you think those humps right there might be? Why do you think that distribution might be bimodal? 1 salt versus 2 salt, right? All of a sudden, coming right out of the data is a significant insight that has not been known anywhere ever in fish biology, right? And that was just from the data, okay? I'll do another example of this. So we don't know for sure it's 1 salt versus 2 salt. If you're a fish biologist, you'd have to dig in and try to make sure that this correlates with other things that you're familiar with, right? And other pieces of information, but at least it's an indication. It gives you an insight. It gives you a direction to look for further knowledge. All right, let's try another one. I have a place in Oregon. I live up there during the summers, and there's a river there called the Williamson River. It's a relatively flat area, and if the Williamson River floods, that would be of significant concern to a lot of ranchers there. And so we just went to the USGS website, got 95 years of data for what's the peak river level every year for 95 years. And if you represent that as a histogram, there it is, okay? If you represent it with a 2-term Metalog or a log normal or anything like that, you're going to get something that looks like that. But what if you go to 4 terms, 6, 8, 10? Now it's beginning to take on the shape of the data and provide some insight. And, I showed this to somebody who had a lot of experience in hydrology. I said, I don't know what this means. He said, well, I can tell you what it means. It has to do with the shape of the river bottom and how fast the river sort of fills up and then it flattens out. And he had a whole explanation for this, but he had never seen anything like this because in hydrology, these distributions are new. Nobody has known that technology like this is available. All right, so that is a couple of guidelines here. I'm going to move into the Excel worksheets in just a second here, but a couple of guidelines. When are the Metalogs most helpful and when they might not add any value? Any situation where you have data, you wish to parameterize a smooth probability distribution with data, They're ideally designed for that. Any situation where you're unsure of which probability distribution to use, because they can represent most anything. Situation in which you like to develop insight about the shape of the data. Those are the examples I just showed. Input distributions for decision analysis or other simulation, because they're closed form for simulation. Smooth graphical displays of the CDF and PDF for any kind of publication, presentation, anything else where you've got data and you want to show it to management or anybody as a smooth distribution. And it's really an alternative to jumpy data CDFs and histograms. You know, histograms are kind of weird because we can go into histograms, but nevertheless, this becomes a nice smooth alternative to histograms if you are so interested. All right, I've already talked about the software implementations. I'm not going to do that. I've got some references and so forth. All of this is in the paper and on the website and whatnot. So now let's go and let's talk about this Metalog workbook. Before I go to the workbook, are there any questions about any of the theory or perspective I just presented? How many of you thought it was relatively clear and you kind of know where we're all coming from? Boy, that's great. I feel great about that. Thank you. Are there any significant questions that yes, Dennis. I wanted the first term, I wanted all the terms to be 0 if y equals 0.5, which that achieves. And so basically, the Metalog is a series expansion around the median of the distribution, and it also gives it the property that the Metalog is agnostic as to whether it's going to be left skewed or right skewed or something else. So that's the reason for that. But you could design quantile parameterized distributions that didn't have that minus 0.5 there, but then you'd have to go off and analyze those properties. Yes? When you said that you're going and fitting, is that directly to the data, or is it dependent upon the way that you quantize the data? And also, I was a little bit confused with respect to, it looks like in order to make it bounded, you need to transform the distribution. That's what you are doing. You are transforming the distribution, just like the log normal is a transformation of the normal. We are doing that. As far as you have a whole set of choices in fitting to data regarding your first question. One is you just put all the data in there, your 3,700 data points, right, or whatever that is, and you can, and because it's a least squares, it's extremely fast. It doesn't matter if it has 3,000 or 30,000 or 300 or 30, right? It's very quick, but you also have a lot of choices. If you want to do some kind of regularization and you wanted to just fit to, 100 equally spaced points on the y-axis out of the 3,400, you could just do that. You could take the percentiles or quantiles and fit to that. And that's a way of regularizing for potential overfitting. Yes?
Yeah. First off, congratulations on what the simplest solutions always are the hardest to come up with, which you alluded to with your 10-year thinking.
Thank you.
Talking about 10, you used 10 terms a whole lot in this presentation, both in your earlier approximations and now for your data. Why?
What I find is that 10 terms is about as much as you'll ever need. Sort of like a Taylor series. If you go beyond 20 terms on some platforms or 15 terms, you'll get into numerical instabilities. But from a practical down-to-earth standpoint, a 10-term Metalog has 8 shape parameters. Compare that to the shape parameters of a beta distribution, which is 2. Okay, you can get so much flexibility with 10 terms. It's just as a practical matter, you usually don't need more. In this spreadsheet I've given you, we go out to 16 terms, but it would be rare that you'd find a situation that you needed that. Great question. Okay, are you guys all ready to go into the spreadsheets here? We have about 12 minutes left according to my clock, so I'm going to need to work fairly quickly, but I also will be around to answer questions and discuss for at least another hour this afternoon. The first page you'll come up with in the workbook is just sort of about this workbook. What I really want to say about the workbook is that, there's required inputs, there's color coding for what kind of inputs they are, what cells you can change. The cells you can change are yellow. These workbooks are self-contained. They contain no macros. They contain no named ranges, okay? And they're completely in native Excel. You can see how easy these equations are to program. What that means is you can safely transport these distributions that I'm going to show you, these other two tabs, into any other Excel workbook that you might already have. You could build your model in this workbook if you wanted to, but you can also transfer them by right-clicking on this sheet name down here, and then you say move or copy. You press I'm going to copy it, and you can copy it to another workbook, and that it will safely copy a whole functional spreadsheet into your other workbook, and it'll retain all of its properties without screwing anything up in your other workbook.
So that means directly you can use an at-risk and crystal ball out of the box.
Right, yeah, absolutely, yes. Okay, so now I'm going to talk about, there are two worksheets here. The first one is what we call the SPT Metalog, SPT, Symmetric Percentile Triplet, a term coined by Eric Bickel and Chris Hadlock. It means that you specify a low probability, like let's say you want your 10, 50, 90. You're going to put a 10% in that low probability box. In fact, I'll just do it right now. Let's give yourself a variable name. Let's call this market size, just for example. And we have a message box over on the side. The message box will guide you through. If you've done something wrong or you're not sure what to do, it'll tell you what you need to do to get a probability distribution out of this. For now, I'm going to say it's unbounded. That's what that U means. The low probability, I'll put in 10%. And so what that does is when you specify the quantiles, the low, median, and high, the Metalog knows that the low corresponds to 10%. The median is by definition the median, the 0.5 quantile. And the high, whatever you put in, is going to be the 90%, whatever is 1 minus the low. So you could put in 0.01, 0.05, whatever you want to. Let's just say hypothetically we've got a market here that the low end of market size is 10. Let's say the high end is 40, and the median, let's say, is 25, just for hypothetical purposes. Okay, we have a Metalog. There it is. And by definition, it's just going to go right through those 3 points, whatever 3 points you specify, right? And then the associated probability density function is what it is. Now let's explore the flexibility of that Metalog. I said there are flexibility limits. What if we said instead it was 20 instead of 25 as the median? Well, now I've got a pretty skewed Metalog, okay? What if I said it was 30? Well, now I've got a Metalog that's skewed the other way. It's just that simple, okay? Now, in terms of limits, how far can it go, okay? Because there's a limit on the 3-term SPT Metalog as to how skewed it can get, and that limit, it turns out, in this case, is around 15. So if you press the button for 15, I pressed 16, let's make it 15, okay. All right, that is the maximum skewness you can get on a 3-term Metalog. Now that's quite a lot of skewness, right? It's not very often you run into things you want them more skewed than that, but if you did, you wouldn't be able to use a 3-term Metalog. You'd have to use a Metalog with more terms, which has even more capability for skewness than that. What's the high end? You could do the high end, I think it's 35 in this case. Yep, there it is. So there's a distribution that's skewed in the other direction. Okay, well there's the boundaries within which you're working. Let's go back to, let's say 20 as your distribution. Now, one other thing I'll say, these are your simulation cells right here. If that's your distribution and you put in your probability y, this could be a random number, but if I say 0.1, what's the 0.1 point on this distribution? Well, it's 10 by definition because it goes through the 10% point. But if I wanted to know what's the 0.05, what's the 5% probability point, then I'd find out that on this distribution it's 7.44. So that's just where you would put your random number if you're going to do a simulation. Pretty simple, okay? Now, what's wrong with this? Well, what's wrong with this is you've got a market size now, and we don't like the fact that it's going below 0. A market size can't be less than 0 and probably shouldn't be. So what would you do? Well, you'd come over here and change this boundedness here. You want it to go through the same quantiles, but instead of being an unbounded Metalog, you want it to be bounded. Okay, now it comes up with a message. What's the message? Well, you have to give it a lower bound. otherwise it doesn't know what the lower bound is, right? So over here, and all of a sudden this cell turns yellow, and let's say your lower bound is 0. All right? Well, there you are. There's your Metalog with a 0 lower bound that exactly preserves that same 10, 50, 90 set of quantiles. All right? Now, another thing you can do with this workbook, this is set up for multiple Metalogs here. So that's Metalog 1. If I copy these cells and paste them down, then I have just put in place a completely new and different Metalog, okay? And we'll call this one, let's say for the moment, we'll call this market share. Could be percentage of oil field that you're harvesting, whatever. I'm going to, for the moment, set it back. Well, here, let's just erase all this. Well, I'm still going to use 1059. Well, I'll use something different. Let's say I'm going to use 5% here. Okay, so I'll use 5, 50, and 95 as my quantiles. Let's get rid of these things for the moment. Backspace, okay. And now if I change this to variable number 2, now it's going to plot my second Metalog there, the market share Metalog. Okay, so what's my message saying? The message is saying, you need to input, what does it say? Oh yeah, you need to input your quantiles. Okay, so let's say you have a market share that goes from, I don't know, let's say 25%, and at the 5% lower bound, and let's say it goes to 40, and let's say it goes to 70%. Oh, wait a minute. It's a market share, so it should be a 0.7, excuse me, and a 0.4, and, oops, point. Oh, sorry. Okay, so thank you. The lower bound in this case should be 0, shouldn't it? Let's say we got, what did I say, 0.25. All right. Let's say 0.4. Let's say 0.7. All right. And okay, now I've got a Metalog distribution. It's a valid one. But you can see that the top of the market share is going beyond 1.0. Well, we don't like that. Market share has to be bounded by definition between 0 and 1, or any percentage on any uncertain variable. So we change this from a semi-bounded distribution to a bounded distribution. That's what the B is. And it says, okay, well then you need to tell me what the upper bound is. So we'll put in an upper bound of 1. And there you have it. Now you have your distribution over market share exactly defined between 0 and 1 and going through the 3 quantiles you've specified. You can do this. You can make this any shape. It's all the shape flexibility passes through these transformations. Yes. So let's go to the Metalog worksheet. Now the Metalog worksheet works completely independently of this SPT Metalog worksheet. So you can copy one of them and leave the other one there, or you can copy this one and leave the other one there. They're not referring to each other in any way. Now this worksheet has a lot more information on it, and that's because it's the completely general case for looking at Metalogs anywhere from 2 terms all the way up to 16 terms. Okay, and I'll show a little bit about how that behaves, and I've also put in, you can see down here, I've put in some sample data just so I don't have to spend time typing data here for the purposes of this little illustration. So one thing I thought about for a moment is, I wonder how far we are from the Denver airport. I don't actually know, but maybe, maybe I think we might be something between 10 and, 10 and 40 miles. Maybe I might think that, right? Well, even that small amount of information is enough to give me a Metalog distribution because it's 2 terms. It's giving me a logistic exactly. But once again, you say, well, yeah, but it can't be negative, the distance. So then you could go up here and change this lower bound here, or this boundedness, to a semi-bounded lower. Change it right there. And then, of course, it asks you for a bound. We'll put in 0. And there you have it. Okay? That's a pretty skewed distribution with a long tail. You might want to decide might want to put an upper bound on that. You might want to flesh out more detail. But really, suppose you were doing expert assessments. Suppose, like for example, I have some example expert assessments right here. If you just put data in this column without specifying any probabilities, it's going to assume that that data is equally likely. So it's specified 25 and 75% as the data for those 2 points I just put in. But if you're doing a real expert assessment in decision analysis, you'd like to be able to specify what y's go with what x's, because that's how you do it if you're using the probability wheel. And so let me copy this, and I'm just going to paste some. There's a user override column there, and I didn't want to do that. I wanted to go edit, paste special values so I don't screw up my formatting here. Okay, there it is. Okay, so now I've put in 4 pieces of data. I've said our expert assessments resulted in, well, plus a 5. I've got a 0 lower bound here. My 10% probability is at 10 miles. My median is at 15. My 90% is at 20. And I've got a 98 percentile, 98% probability on it being less than 25 miles. Okay, I don't know what the real number is. It doesn't matter for this illustration. What I want to show you, though, is I've got a 4-term Metalog, and it goes through all of these points. If you have the same number of terms as data points, the Metalog, if it's feasible, will always go through all of those points exactly, not approximately. However, if you give it inconsistent points, so suppose I said this 25 miles, instead of being at the 98 probability, is also at the 90 probability. Now, that's actually inconsistent even, right? You can't have both 20 miles and 25 miles being at the 90, well, you could, I guess, 90 probability. But what you can see up there is what I was expecting to see. Oh, I didn't type the 90, 0.90, enter. Okay, so you can't read it. That's okay. But anyway, what you would see if you could read it is now the Metalog is not going exactly through all 4 points, and I've got 2 points up there on either side, and the Metalog is kind of splitting the difference between the two, which it does, of course, because it's fitting it by least squares to the data. You can put any number of inconsistent data in there you want, and the Metalog is just going to run a curve right through them, so long as it's feasible. All right.
So maybe sort of start rounding up here.
Okay, so can I have 3 minutes? Is that okay? So let's take another data set. And I'm going to quickly go through these now. Let's take the height of the Williamson River data set. That's the same 95 points that I just showed you. And let's see if I can get up here. Okay, edit special values, put those in there. Those are equally likely data points. And oh goodness, what happened here? Oh, I've got these 10, 50, 90s. I need to erase those because those are all equally likely. These data points are all equally likely. Look at what happens with your this set of graphs on the right is called a Metalog panel, and it shows you what your Metalog looks like for any number of terms. So this is if you represented that data with 2 terms, you get that distribution: 3, 4, 5, 6, 7, 8, 9, 10, and so forth. You can see how the Metalog is shaping itself to the data the more terms you add. And then whatever number of terms you put in this box, let's say this is the 10 terms, there we are.
Okay.
Okay? Are we over? Or
No, we're right on time. We just
Okay.
need to move forward.
okay, I'm going to move forward. I'm going to hit one more data set, and then we're going to quit. This data set is the one, but it's important because you need to understand about overfitting, okay? This is the data set that we used. Oh, come on, data. Oh, shucks. Well, maybe I'm not. What
Let's
I'm
give a few more questions.
Okay,
And
that's
then
fine. I was going to show you an example of overfitting, and if you put data in there and you fit too many terms to it, you'll get some wavy artifacts, and so you ultimately just need to make a judgment about how many terms you want to have. That's the key point. Okay.
So how would you, or would you use this in like a maximum likelihood context, like a regression or something?
Well, well, first of all, if you had normality, the least squares solution is the maximum likelihood solution. But you don't actually have normality here, right? You have something that's close to it if you have a lot of data. To calculate maximum likelihood here is kind of challenging because you've got the inverse form, and you'd have to solve that. For each x, you'd have to solve for the y and then plug it in. It can be done. You just have to iterate to do it. And by the way, with the maximum likelihood, you get results that are very close to what you get if you just use the simple least squares method. In almost all cases. Yeah. Okay. Any other questions?
So if you have 3 distributions you wanted to add and multiply or divide those variables, you just do it and then you get...
You just do it in Excel. You add, subtract, multiply the
gotta-
variables, do your simulation, and then hook up another Metalog to the simulation results,
And
right?
it's a closed form solution for those?
No, the addition isn't closed.
Oh, no, the addition, no,
Or
the,
some simulation to do that.
you would need some simulation to do if you're talking about the sum of 2 independent random variables, you
Right.
still would need to simulate that, or else you would need to use what I haven't shown, which is the separate Metalog formulation, where you, for independent variables, you could add together means, variances, and skewness, and use a Metalog parameterized by those to get a closed form solution.
Or the sum of log normals.
Yeah, the sum, yeah, right.
Jay?
Tom, this is amazing stuff, and I feel like we're just touching the tip of the iceberg. I just had a question, not for you, but for the people here. If we offered a half-day workshop next year's DAG, where Tom was able to spend a whole half day on this, how many people would show up for that workshop? I'm not trying to put any pressure on you, Tom, but
Okay.
just wanted to put that show of hands. Okay, thank you.
Hi, Tom. So if
Yeah.
we were planning to use other software to perform our simulation,
Sure.
can we recover the complete equation of the Metalog with all the parameters so that we can go and transfer it to our other software
Absolutely.
package?
All you have to do is click on that cell there, and you'll see the equation. It's just sitting right there, and you'll see the,
Which cell?
pardon me?
For
sorry.
example, MATLAB. If I
Well,
wanted
on the
MATLAB, for
SPT
example.
Metalog worksheet, you would click on this CDF cell, given the probability.
Okay.
And you'll see in there a formula that basically takes you right through. The formulas are also on the website and in the paper, so the formulas are easy to
Yeah,
find.
but I want my parameters. That's what I'm.
Yeah,
I mean,
the-
I understand that we can get the formulas from the paper.
The parameters, let's see, this is, oh gosh, I don't know what's happening here. I can show you afterwards, but the bottom line is that the parameters are there, and I can't get my computer to go up. Oh, yes, I can. Okay. So the parameters here are all your A constants right here. Okay? And on the SPT sheet, they're there also.
Okay, thanks. I think I would like to ask Sam now to make an announcement.
Yeah. Okay, so I'm Sam Savage, Executive Director of probabilitymanagement.org. Geek is a necessary definition for Tom, but not sufficient. Entrepreneur, necessary, but not sufficient. Consultant, necessary. But are you aware this guy was almost a professional golfer? Plus all the dimensions I don't know about yet. So I've been thinking about, Renaissance man is the thing, probably the safest bet if you want to talk about Tom. But anyway, he is giving a webinar for us at probabilitymanagement.org. If you don't know about us, we're trying to do for uncertainty what Arabic numerals did for numbers. And Metalogs are going to play a big role in this. We charge for our webinars, but for you folks, if you email Tom or me, we're going to give you a free pass for webinars coming up in June sometime, right, Tom?
I think it's in early May,
Well,
or
come-
late
we'll-
April, something
We'll
like that.
email you the free passcode.
So send him or
Should we
me
write
an
those
email
email
if you like.
addresses
Yeah.
down over here?
Pardon me?
Should we write the addresses down? Do we have a marker?
Are there,
While I do that, I
Well,
would
since-
like to thank Tom very much for this very inspiring presentation.